Now, we have seen that G1 doesn't have any open subgroup of infinite index. This means that also G1 does not have any infinite discrete quotients. Because in a sense, a subgroup, an open subgroup of infinite indexes precisely corresponds precisely to some discrete quotient, infinite discrete quotient. So if we take a quotient by an open subgroup, we obtain something discrete, and vice versa. If we have some discrete quotient, then the per image of 0 is an open subgroup in G1, and it has infinitely many cosets because this quotient is infinite. So this implies that G1 doesn't have an infinite discrete quotient subgroup. All discrete quotient subgroups of G1 are finite, and when we dualize this, then we really obtain that gamma 1. So gamma 1 is the dual of G1. G1 has no infinite discrete quotients, so gamma 1 has no infinite discrete compact subgroups. Okay? So by duality, we obtain this. Gamma 1 has no infinite discrete compact subgroups. Since we have proved that, then gamma 0 also doesn't have any discrete closed compact subgroups, and we are precisely under the conditions of this lemma 3 which I erased, and so it follows that well, what does it follow? Well, maybe I can erase lemma 2. Okay, so it follows that this subgroup gamma 0 is equal to Rn by lemma 3. Okay. So now we see that so gamma 1 contains Rn as an open subgroup. Now it remains to prove the following claim. Gamma 1 is equal to the direct sum of L1 and some discrete group. Indeed, if we prove this, then we recall what gamma 1 is. Gamma 1 is the dual of G1. So we dualize this relation, and we obtain that G1 it is equal to the dual of gamma 1 is equal to the direct sum of the duals here. But the dual of R1, Rn is also Rn, and here the group lambda hat will appear, and lambda is discrete, so lambda hat is compact. So this is precisely the claim of our theorem, because what happened, we started with some group G, and we have obtained an open subgroup G1 in it, which splits in the sum of Rn and something compact. And this is precisely what was needed in this theorem. So now we only need to prove that the following decomposition holds. So the last point in this argument. Okay. Now we prove the claim. Let lambda be a maximal subgroup of G of gamma 1 such that lambda 1 intersects this subgroup R1, Rn only by 0. So such a maximal subgroup clearly exists by its own lemma. First we claim that lambda is discrete necessarily. So statement 1, then lambda is discrete. Consider subsets, cosets of gamma 1 relative to this subgroup R1. I recall that it is open. So consider such subsets, and then we see that lambda may intersect each such subset by at most one point. Each such coset by at most one point, because otherwise there would be something non-zero in this intersection. If there are 2 points in some coset, then there are differences in lambda, and it is non-zero. So the intersection of lambda, which is with this, each coset of Rn here, is at most a singleton, and so lambda is discrete. Every its point has a neighborhood precisely the coset it is contained in, which is open, has a neighborhood that doesn't contain other points of lambda 0. So lambda is discrete necessarily. Next, which is also clear, the sum is direct. Because algebraically this is quite clear because of this condition, and topological condition here is void because lambda is discrete. So this is a direct sum. And the last thing, which is the most difficult, is that Rn plus lambda is equal to gamma 1. If you show this, then the claim is proved. So the proof of 3 is by contradiction. suppose 3 is not true, that is, there is gamma in gamma 1, so that gamma doesn't belong to Rn plus lambda. Then there will be some contradiction with the maximality of the subgroup lambda. We show that if such a gamma exists, then lambda is not maximal. Lambda can be extended a little bit. Okay, and this will finish the proof. But this is not very difficult, but somehow is not also immediate. Now consider the set of multiples of gamma, where k is an integer and k is not equal to 0. Let's try to extend our group lambda. So let okay, maybe even I don't restrict this set of k by k non-zero. So consider this set of multiples of gamma and consider the group lambda tilde is the group generated by lambda and gamma. Of course, this gamma is not in lambda because it is even not here. So consider the group generated by lambda and gamma, if so this is something which is strictly greater than lambda because it contains gamma, but gamma is not in lambda. Suppose that k gamma well, how to say this in some nice way. Okay, let's do this formally. Each element of this subgroup of lambda are of the form k gamma plus beta, where k is in z and beta is in lambda. Okay, so this group is formed by these elements, and since it is strictly greater than lambda, it doesn't have this property. It doesn't have this property because lambda is maximal with this property. So there is k, and this k is necessarily non-zero because otherwise this element is in lambda, so that k gamma plus beta is in this group is in Rn and is not zero. Okay. So there is some element k which is non-zero and some element beta in lambda, so that this thing is in Rn and non-zero, and x is non-zero. Well, because otherwise we can extend our subgroup lambda with preservation of the same property. Otherwise, lambda tilde would be a subgroup which is greater and has the same property. So we have this. We have this. Okay. Okay. Now put y equal to x divided by k, which is possible because we are in Rn and Rn is divisible. And take the following element: gamma 1 is equal to gamma minus y. Then what's about k gamma 1? K gamma 1 is equal to gamma minus x and gamma and this is k gamma minus x, k gamma minus x, and k gamma minus x is some element of lambda minus beta, and this is in lambda. So this is in lambda. But still gamma 1 does not belong to Rn plus lambda, because otherwise gamma 1 is equal to otherwise gamma 1 is this element gamma minus y, so gamma minus y is equal to lambda 0 plus w, where this element is in lambda and this element is in Rn. From this we can solve this equation for gamma. So gamma is equal to y plus w plus lambda 0, and this is a contradiction because gamma was not in the sum of this group. So this is in Rn and this is in lambda, and gamma was not in the sum of these two groups. Here it is. So still this element gamma 1 is not in lambda, in Rn plus lambda. So, the point is that this gamma 1 is a little bit better than gamma. We again do the same trick with it as with gamma. So we know that it is not in the sum of Rn plus lambda, then by the same argument as before, there is m in z, which is not 0, and there is z in Rn, which is also not 0, so that and also there is gamma 2 in lambda, so that gamma 2 plus m gamma 1 is equal to z. Okay. Not gamma 2, but probably alpha. Alpha. There is some alpha in lambda. So that we have this inclusion. This alpha plays the role of beta as the previous step. Again, the same. Some multiple of this element, gamma 1, which is not in sum, plus some element of lambda must be in Rn. And this thing is Rn must be non-zero. Then let's multiply this by k. K alpha plus k m gamma 1 is equal to k z. And this is still non-zero because in Rn multiplication by an integer cannot lead to annihilation of something. So this integer is non-zero, z is also non-zero, so this is non-zero. This is non-zero. But what? But alpha is in lambda, and k gamma 1 is also in lambda, where this is written. Here it is k gamma 1, turns out to be in lambda. So we look here, we have here something in lambda, and here m times something in lambda. This means that this is in lambda. On the other hand, this is in Rn and is not zero. And this is a contradiction. Because lambda intersected with Rn is 0. And so that's all. The structure theorem is proved. Okay. Well, let me remind you what we have proved. So the statement of the theorem is as follows: G, a locally compact abelian group. Then there is an open subgroup G1 in G, so that G1 is the direct sum of Rn plus something compact, plus say K, where K is a compact. Group. Last time I told you that it is interesting to think a little bit about this quotient G by G1. So this quotient is discrete. So topologically, everything which is interesting here in this group happens within this subgroup G1. But again, topologically, this G is the disjoint union of cassettes modulo G1, and all of them are open and closed, so topologically the structure is quite clear, but algebraically it is not so, because well, it may happen that G does not split in a direct sum of G1 and something discrete. Well, so if I consider this quotient, then maybe there is no section for this quotient, and so algebraic structure may be somewhat involved here. And there is a very old example due to Kaplansky when this happens. It is simple. Well, of course, also it should be noted probably that this group G1 can be obtained in a variety of ways. There is no canonical way to produce such a group G1. There are many ways in principle, but still this clarifies the structure of the initial group. But now, as to a counterexample to this conjecture that maybe this quotient map also has a section. So the example looks like this. Consider the group Z4. This is a group of integers modulo 4. It consists of 4 elements, and the addition is modulo 4. Now G will be something like product of this countably many copies of this Z4, but in a bit strange product. So let G, for the moment I don't define any topology on G, just as a set, it is the collection of all sequences zeta n, so that only finitely many zeta n's are equal to 1 or 3. So this is a sort of semi-complete product, so to say. We allow any values of zeta n if they are not equal to 1 or 3, if they are 0, 1, 2, 3, this way. If they are equal to 0 or 2, they may be arbitrary. But if they are equal to 1 or 3, there must be only finitely many such places in which they are equal to 1 or 3. Well, something intermediate between the complete product and the direct product. Now let K be the subgroup of G consisting of all x for which 2x is equal to 0, that is Cn is either 0 or 2 for every n. And we can view this K as a compact group, namely this can be viewed as a dyadic group. The group are isomorphic to the complete product of pairs of Z2. To define a topology here in G, declare K open in G. So this determines uniquely a topology in G, and under this topology, G will be a locally compact abelian group, of course. Now, I don't want to check all the details of what will happen. Take a compact G1 in G, open compact. Here it will be necessarily compact because clearly this cannot contain anything like Rn, so this G1 from the theorem must be compact, as in the theorem, the structure theorem. Then what happens? Then G over G1 is discrete as usual. If there is a section, if G is a direct sum of G1 and this discrete subgroup, then G itself has an infinite discrete subgroup. But this is impossible here because simply every infinite subgroup of G has an infinite intersection with K. This is fairly easy to see. And so if we have a discrete subgroup which is infinite, then its intersection with K is also infinite, but K is compact, and so it cannot be infinite. So in this situation, independent of how we select the subgroup G1, there will not be a direct sum of G1 and something as a result. Okay. Well, at this point, let me stop with the general theory of locally compact abelian groups, and let us explore some details about non-commutative locally compact groups. Namely, I promised to prove the Peter-Weil theorem and some of its consequences, and let me do this now. Well, for some reasons I want to avoid the discussion of representations, well, at least to a great extent. Surely some words about representations will be said, but I want to start with a form of the Peter-Weil theorem, which does not mention the representation theory. Well, and this theorem has something to do with characters, which I discussed it so much time before. But, okay. Now let this time G be a compact group, not necessarily abelian. Here I suppose that G is compact because in the locally compact setting everything becomes much more complicated, bulky, and involved. But in the compact setting it is reasonably short and clear, so let's restrict ourselves to the compact case. Okay, then let f be some function on G. Then I consider the right shift of f. This is a function defined this way. At the very beginning of our course, we considered, it seems to me, left shifts, and even we wrote somewhere s to the power -1, but in fact all of that is more or less the same, so consider right shifts this time. Now, definition. F is said to be finite dimensional if the linear span of the shifts of f is a finite dimensional subspace, is a finite dimensional space. So we take a function, consider all its shifts, and consider the closed linear span. If we obtain a finite dimensional subspace this way, then our function is called finite dimensional. So the better Weil theorem claims the following. So there are two statements. First, the set of all square summable not quite. Square summable is not. So this is true, but let me state it another. The set of all continuous finite dimensional functions is dense in the set of continuous functions on G, and dense, okay then, yes, and in L2 of G. Here L2 of G denotes the space of 2 against the Haar measure. Since our group is compact, there is no difference between left and right Haar measures, and the modular function is equal to 1. So our Haar measure is simultaneously right invariant and left invariant. And of course, the first claim that this set is dense here implies the second claim that the set is dense in L2, because the set of all continuous functions on G is dense in L2. Surely. But the point is that this statement about L2 is very important first, and second, it will be proved first. So the order will be as follows. We first prove that continuous finite dimensional functions are dense here, and then we shall prove that they are dense here. Those who know this from the side of representation theory maybe don't recognize the Peter-Weyl theorem as it is stated there. But in fact, this is the same, and probably we shall see it at least on certain examples. Now, in the proof I shall use convolutions, and we discuss convolutions only for commutative, for abelian groups, locally compact abelian groups. Here, in the non-abelian case, the theory is quite similar. The only thing we should remember of is the fact that there are left convolutions and right convolutions. So we should not mix up multiplications from the left and from the right. So we should argue with some care when we convolve functions and make some estimates. Probably I will not even state general theorems about convolutions, but in some cases I will repeat calculations. In some cases which I shall need, I will repeat calculations. Okay. So we start with the proof of the fact that the set of all finite dimensional and continuous functions is dense in L2. That N be the orthogonal complement of the set of all finite dimensional continuous functions. So we must prove that this space N consists of 0 only. If the orthogonal complement is 0, so the set to which we make this orthogonal complement is dense in L2, so this will be the end of the proof if we prove this. And to do this, it suffices to prove that all continuous functions are orthogonal to N. Again, because continuous functions are dense in L2, so it suffices to prove this, but so look at the outline of this proof of the method. So for the moment, we even don't know if finite dimensional functions exist. The scheme of the proof is as follows. We suppose we have some function in N that is something orthogonal to all finite dimensional continuous functions, and then without the knowledge that they exist, we want to prove that this thing is orthogonal to all continuous functions. So there is something tricky maybe in the approach to this problem, but anyway this works. We'll see that this works. For this, let's recall the involution for functions on G. This is something we came across already. F tilde of S is equal to F of S to the power minus 1 bar. So F is a complex valued function on G. We form this function, and it is called, it's denoted by F tilde. So this operation mapping F to F tilde is an involution, because if you do this twice, then we obtain F again. Now, suppose F is a continuous function, then f is represented in the following way, where h and g are Hermitian elements with respect to this involution. Simply take h equal to f plus f tilde over 2, and g is 1/2 of f minus f tilde over I. So surely we have the following representation. If I multiply this by I and then add, I obtain f. This is clear. And the point is that both h and g are Hermitian with respect to this involution. That is, h tilde is equal to h, and g tilde is equal to g. If I take f tilde, I obtain f tilde tilde plus f tilde plus f tilde tilde, and f tilde tilde is f itself. So h tilde is equal to h, and here it is the same, because if I apply tilde to this difference, I obtain the same difference but with a minus sign, but also I have imaginary unity here, and because of this complex conjugation, I obtain another minus sign here. So g tilde is also equal to g tilde. Now, these elements are Hermitian against this involution. This term, maybe I even don't use it, is a sequel, but the consequence is that it suffices to prove that if G belongs to C of G and G is equal to G tilde, then G is orthogonal to N. Because if we prove that G is orthogonal to all Hermitian element in the space of continuous functions, then from this representation it will follow that it is orthogonal to all continuous functions, and then N is equal to 0. Okay. Why did I insist that my function be Hermitian? Why did I insist on this property? This is because then the convolution with this function g is a self-adjoint operator on the Hilbert space L2, and we shall apply the spectral theorem to this self-adjoint operator. And from this spectral theorem, everything will be clear finally. So for f in L2 of G against the Haar measure, we define the operator Tg, and G is again a continuous function which is Hermitian, which satisfies this relation. Tg f of S is a so-called right convolution, the integral over G of little g S u to the power minus 1 f of u du. Okay. Well, some remarks about this convolution. This time, of course, you recognize here the usual formula for convolution, but this time this operation is not commutative, of course, because if I declare this a new variable, then you see that I transform this right convolution to a left convolution. To a left convolution. So this is not commutative, of course, but still, this is a linear operator. This is a linear operation. This is linear in F, and so the claim, which is quite essential in what follows, Tg is a compact operator from L2 of G to C of G, and consequently to L2 of G also. So probably it's claim 1 and claim 2. Tg is self-adjoint. On L2 of G. So what happens here? In fact, this operator acts from L2 of G to the space of continuous functions. We shall see this. And moreover, it will be compact as an operator from L2 to C. But we can also treat it as an operator from L2 to L2 because C is included in L2. And because, and since this space is included continuously in L2, then this operator automatically will be compact as an operator from L2 to itself. And moreover, it turns out to be self-adjoint on the space L2 as an operator from L2 to itself. And then by the spectral theorem, it will decompose in the Schmidt series. And when we decompose it in the Schmidt series, we will be nearly at the end of the proof of the Peter-Weyl theorem. Okay, so these are two crucial auxiliary statements. Okay. Now how to prove the first claim? White is compact from L2 to C on G. This follows again from counter type, almost absolutely continuity theorem, and we even proved such a statement at the very beginning of our course. Let me probably formulate not that statement because that was very general. There were some neighborhoods and some list of properties, and okay, it was designed so that it would be easy to apply that statement in the situation we needed it for the construction of the Hauer measure. But here we need something much more modest. So the proof of claim 1. Let epsilon be positive, then there exists an open neighborhood U of unity in G, so that whenever st to the power minus 1 is in U, we have the following inequality: G of S minus G of T is smaller than epsilon. So I remind you that G is a continuous function, which is also Hermitian. This was this relation, but right now I don't need this relation. It suffices only to have a continuous function G, to have this. And well, okay, I don't prove this because this is standard, and we saw something like that. This is done in the standard way. Simply, by some open covering of the group G by some shift to a small neighborhood of 0. Well, anyway, this is true. So take this neighborhood of unity, and also take f in L2 of G with the norm of f in L2 at most 1. So take f in the unit ball of L2. So I will show that the entire family of functions of this sort, where f runs through the unit ball of L2 and G is fixed, the entire family is uniformly equicontinuous. Okay, so let S t minus 1 be in this neighborhood U, then we write this difference. We estimate the continuity modulus, so to say, of the result of application of operator Tg. What is this? We use this formula, and it is the integral of a G of little g s u to the power minus 1 minus G of t u to the power minus 1 f of u du. Okay, but here again we have two elements whose quotient is in U. Not quite the quotient, but let's look at it. So here we have one argument as u to the power minus 1, and here we have t u to the power minus 1. And if we put minus 1 here, we obtain as u power minus 1, u t power is minus 1, that is as t to the power minus 1, and this is now a neighborhood capital U. So we have here two arguments, so that this combination of them belongs to U, and this means that this difference is less than or equal to epsilon in modulus. So the modulus of t g f of s minus t g f of little t is less than or equal to epsilon is the integral over g, the modulus of f of u du. And here the L1 norm is dominated by the L2 norm, because the Haar measure on a compact group is normalized probability measure. So then it follows that You have the following inequality for all f in L2 of G. Well, and if we assume that the norm of f in L2 is in post 1, where it is, I wrote this somewhere. I wrote this somewhere here. So this is simply at most epsilon. And now we see that the image of the unit ball of L2 under the separator is equicontinuous in the uniform metric. First, not only all functions in this image are continuous, well, but even they are equicontinuous, and this means that the separator is compact. Really, it is compact from here to here. And now we should verify the second claim, that it is self-adjoint. Well, this is a very simple calculation, and this follows from the Hermite property of the Hermitian property of the function g. Let me probably erase. This. Okay, so let's consider the scalar product of f1 times tg of f2, where f1 and f1 and f2 are some functions in L2. Well, let's write out this expression. This is f1 of s, and here I should write tg of f2 of s bar. Okay, tg of f2 of s, this is the following guy. So all of this should go with bar because of the definition of the scalar product in L2, and this is integrated by s. Now we change the order of integration. We put this bar down under the integral sign, and then change the order of integration. So what emerges, the integral over g f2 of t bar. This comes from here. The integral over g g s t to the power minus 1 bar f1 of s ds. Okay, so everything is consistent for the moment, and here also dt. Everything is consistent for the moment because the only terms with bar is this one, which is here, and this one, which is here, and f1 is without bar, so we simply change the order of integration. And now our function g is Hermitian, so g of u is equal to g of u minus 1 bar. Okay? So we can replace this guy in accordance with this formula, and we obtain the integral over g of f2 of t bar, and here is the integral over g of little g of t s to the power minus 1 f1 of s ds dt, and clearly this is tg of f1 without bar, and here we have f2 with bar, so this is tg applied to f1, f2. Then when we calculate the scalar products of such functions, we can transfer the operator tg from the second scalar factor to the first one, so it is self-adjoint. Okay, on L2, as an operator on L2, of course. And now we apply the spectral theorem to it. It is a self-adjoint operator in L2, and also it is compact. So it has a countable number of real eigenvalues. Some of them are non-zero. Probably there is a zero eigenvalue. And also the eigenspaces corresponding to non-zero eigenvalues are finite dimensional. Okay, so let's write all this down. By the spectral theorem, T has n at most infinitely many, accountably many. Many non-zero eigenvalues. Lambda g, all are real. The corresponding eigenspaces are finite dimensional. Mutually orthogonal. And all of them orthogonal also to the kernel of Tg. Well, in general, if we have a self-adjoint operator, then its eigenspaces are orthogonal, even no matter what the value of the eigenvalue is, zero and non-zero. And the kernel of the operator is precisely the eigenspace corresponding to the zero eigenvalue. So this is also orthogonal to other eigenvalues, and moreover, all eigenspaces including this kernel form a direct decomposition of the entire Hilbert space L2. FL12G. Okay. So now what's about these eigenspaces? First, we treat the eigenspaces corresponding to non-zero eigenvalues. Suppose that we have an eigenvector corresponding to some non-zero eigenvalue. I remind you that lambda g is not equal to 0. Moreover, I did not tell that the only possible accumulation point of this lambda j is 0, but probably this will not be required in the proof. But so let's forget about that. So suppose we have this, and this is non-zero. Then what do we have? This function is continuous. We know that Tg maps L2 into the space of continuous functions, and lambda is non-zero. So all such eigenfunctions are continuous. Phi is in C of G. Now let's write this relation in detail. Well, I write what Tg is. So this integral we write this in detail. Lambda j phi of s. And now here let's replace here s by st. T is another parameter, another element of the group. So let me just write t here. Clearly, this is also true for trivial reasons. Well, and now we make a change of variables. We replace u by ut and use the invariance of the Haar measure. So ut here will be t minus 1, u minus 1. So we obtain the integral over g of little g of s u to the power minus 1 phi at of ut du equals lambda phi of st. And this means that the shift of phi by t is also an eigenfunction corresponding to this eigenvalue lambda j. Now the shift does not lead us out of this space, this eigenspace corresponding to the lambda j. And I remind you that this space is finite dimensional. This means that every eigenfunction of my operator corresponding to a non-zero eigenvalue is a finite dimensional function. Okay, phi is finite dimensional. Well, and since phi is finite dimensional, so still we found some finite dimensional function. We did not know that they exist, but in fact they exist by the spectral theorem. And by assumption, phi is orthogonal to n. Okay. So all eigenfunctions are orthogonal to n. All eigenfunctions corresponding to non-zero eigenvalues are orthogonal to n. And our space L2 is the orthogonal sum of these eigenspaces corresponding to non-zero eigenvalues and the kernel of T, G. Okay? So it follows that the consequence is that n must be included in the kernel of Tg. So let's write what this means. Take h in n, then Tg of h is equal to 0. And what does this mean? We have a formula for Tg. So 0 is equal to the integral over g of little g s to the power of u minus 1 h of u du. And again we use that little g is Hermitian, so simply write this in this way: g of u s to the power minus 1 bar h of u du. It's useful to write it in this way. So this integral is equal to 0 for every s. For every s, and here just put s equal to the unity of our group. Then this relation shows us that h is orthogonal to g simply. So we have obtained that any element of n is orthogonal to all Hermitian continuous functions. Hence, it is orthogonal to all continuous functions. Hence, it is equal to 0. So what we have proved? We have proved that the finite dimensional functions form a dense subset of the set L2. Continuous finite dimensional functions form a dense subset of L2. Now it remains to prove that they also form a dense subset of the space of continuous functions of the group G, but this will be the next time.